So there's this wonderful game on the App Store called Flows Free. And Flows is basically a puzzle game where you're given a grid and the grid is filled with different colored dots. And what you're trying to do is you're trying to draw a path so that you're connecting the two dots of the same colors together. So sort of like what I'm showing you here. Now the game is really simple, but also really addictive. And I don't want to brag or anything, but I currently have a daily streak with that game of about 1,100 days, which comes out to just a bit over 3 years. Lasts a lot longer than some of the Snapchat streaks I used to have. And sometimes I even post it on Facebook, and I'm just gonna say some of my friends get pretty jealous of that achievement of mine. And it's a lot of fun, but sometimes it does get a little bit difficult. And it occurred to me that maybe I should try to find a way to get someone else to solve the game for me. Specifically, maybe I should write a piece of code that will do this solving for me. And so I had the idea of making a solver for this game. And then I made it. So it looks like this. I can just give it an image from the game, I can press run, and then it will just draw out the complete grid for me like so. Now the big question that I want to try to answer in this video is, how do I do that? And in order to explain so, let's draw it out on a piece of paper a bit more clearly. So let's suppose we look at this particular board that I have on screen here. How else can I display this maybe in a way that will be a bit more helpful to our thinking? Well, this board is a 5x5 board, and each of the square is supposed to be filled with a line. So I'm going to draw it like this. I'm going to suppose we have 5x5 dotted grids. It looks something like that. And some of the dots are painted. So for example, this dot will be painted red. This is according to the problem itself. So in the end it looks like that. Note that I used a different color here because I didn't have a green pen. One way you can think about it is that each of the dots have got lines connecting it with adjacent dots, like so. And each of these lines that we have are possible places where you can draw a connection between each of the colored dots. And what you're trying to do is you're trying to draw the connection so that you're connecting the same colored dots together. So red might have lines drawn over these particular edges. So, as you can see there, a bit unclear, but the whole point is we are given this arrangement of dots and we're trying to find how we can paint, how we can color in these different lines so that these dots are connected and that the same colored dots are all connected like so. Now some people out there might look at this and instantly say or instantly recognize that this will be some sort of a graph problem. Now to a couple of other people, you'd probably be wondering, what is a graph? People might think of graphs looking something like this, being, you know, like two axes and maybe some bars, all those sorts of stuff, something like that, right? This is not the graph we're going to be talking about. We're going to be talking about a different type of graph that you find in discrete mathematics. So what is a graph in that sense? Well, mathematically, in the most abstract sense, graphs contain two things. Graphs, which I can call G, is a set of two different things, a set of what we call vertices and edges, like so. Vertices can think of as different nodes, as different points, and edges being how we represent each nodes being connected to one another. So I am going to show this in a bit more geometric manner, right? So because it's a bit difficult if I write it that way. So first we have the vertices, and you can think of vertices as just dots in space. Note that it's a lot more abstract than this, but I think this way of thinking is probably going to be the most abstract, the most concrete, sorry. So maybe we have vertices looking something like that. Those are just points in space for our case. And then when we have vertices, we're also going to have edges, and these edges will connect each of the vertices together. So for example, we might have a connection between these two vertices, and these two might be connected to each other. And so in the end, we might have something looking a bit like this. So we can see that the red dots represent the vertices, and the blue lines here represent each of the edges. Now, as I mentioned, graphs are very abstract things, and it might not just be things represented geometrically like this. Maybe, for example, your vertices might be people on Facebook, and edges might be the people who are friends with each other. So this might be a friend with this person, and you can show that by having two edges connect to each other. Or maybe you might say that each of the vertices is a town, and the edge is connected if the two towns are connected to each other, for example. So if we take this graph and we compare it to this diagram that we have earlier, we can see that possibly there is some connection between the two, because this is a set of vertices with edges between each other, and this one you can think of as many vertices with edges connected to each other. So maybe this is a graph, and if you can find ways to solve things with graphs, maybe you can use it on here as well. And so what I continue to do is just look at this problem from a graph point of view, trying to find a way, finding an algorithm that will help me be able to solve this problem using some graph theory. And also for you guys out there at home, I encourage you to pause and ponder upon this problem and see how you might want to approach this problem. Now, I thought pretty hard about this problem. I didn't really get too far trying to find a graph theory-ish solution. Maybe someone out there will be able to find it. If you are, I don't know, my algorithms teacher, you might also know how to solve this. In that case, good job. But I never figured it out, and so I turned to a totally different approach, and it's an approach using something called linear programming. Now, linear programming doesn't sound like anything to do with graphs, and in fact, it has very little to do with graphs. Well, the question we can ask now is, what is a linear program? Well, linear program is a concept in mathematical optimization, and it's a form of what we call a mathematical model, a way we can express optimization problems mathematically. So this is the setup for a linear program. Note there are many other types of optimization problems. Linear programs is just one of them. So in linear programs, we're going to have different variables. So we're going to call these variables, for example, x1, x2, x3, all the way to xn. Now, when we optimize something, we have an objective, a particular goal we want to try to have. So in this case, we're going to say the objective is to maximize something. We're going to try to maximize this particular combination. We're going to maximize c1x1 plus c2x2 plus all the way to Cn xn. Maximizing objectives might be, for example, we want to maximize profit. So this will be the expression for your profit. What are you trying to maximize in your optimization problem? You can note here that it is, in fact, a linear equation, which is why it's called linear programming. But when you optimize things, well, most of the time you are not just trying to vary x however you want. Usually there are constraints, what you can do and what you can't do. So we usually say this is subject to some constraints. And the constraints we have will be written in the form of a11x1 plus a12x2 plus all the way to a1n xn is going to be less than b1. A11, A12, all of these numbers are just constants, and so is B1, and in fact so is C1. And we're in fact going to have this for however many terms. We might have like some number of equations, maybe like k equations of these or something, depending on how long your constraint is, how big your constraint is. So this is what we call a constraint. Basically, you're saying you can vary x however you like, but you have to be within this limit, within this variable b. This is a constraint. And usually they also put another constraint on, which is to say that your x1 must be greater than 0, your x2 must also be greater than 0, and in fact all your x's, all your variables must all be greater than 0. And this is what we call a linear program, because all the equations here, this equation, and in fact even this equation, they are all linear. Now usually another constraint that people usually put on is they also make sure that all of your variables can be any real number. Sometimes you only allow it to be an integer, for example, but that's also a different case altogether. And usually you don't write your linear program as sums like this because it's a bit messy. Instead, you use more linear algebra notation. So your variables, rather than writing it out as a list like this, you just use one vector, and the objective function, rather than writing it out as a linear combination, it can be written out as a dot product. And your constraints can be written as a matrix A multiplied by your variables must be less than some constant vector like such. I'm not going to go into detail that these two are in fact equivalent. See linear algebra textbook. And there is so much more as well to talk about linear programs, such as this constraint here. If you draw it out graphically, you get a polyhedra, or in 2 dimensions, it would just be a polygon, or duality of linear programs, all those different sort of things, which we're not going to have time to go through. So I encourage you to go out there and read a bit more about it. Now, linear programming, as I've shown here, is actually a very broad problem in the sense that you can probably apply it to many different sort of things. Now, there are ways to solve linear programs. One of the ways is the simplex method. I won't talk too much about what these are, but all you have to know about these methods is that it solves linear programs, but it's also incredibly slow. Now, as I said, linear programs are pretty versatile. You can use it to solve many classes of problems. The key place you use it is in optimization problems. For example, if you're a construction company and you have a limited number of resources and you want to make some different amount of things, what's the best combination of things to make? Those sorts of problems can be phrased as a linear program, and then you can solve it using the simplex or the interior point methods I've mentioned. But what if we try to use linear programs to solve graph problems? Stop the music, please. Thank you. But really though, let's try to consider what it looks like if I want to use linear programs into solving actual graph problems. And as an example, I'll be using a different graph problem from the one with flows. I'll use a simpler graph problem. We're going to consider a problem called the max flow problem. I'm going to try to phrase this in terms of graphs, and so in order to do so, I'm first going to start by drawing a graph. So in our graphs, of course, we're going to have many different vertices. So I'll just draw the vertices out like so. Now we have different vertices, and now I'm going to draw a couple of edges in there, but the edges that we're going to draw is going to be slightly different from the ones that we have drawn previously. Firstly, we're going to have something called a directed graph rather than an undirected graph. And what I mean by this is that an edge doesn't just connect two vertices together, but also specifies a direction. The rest of the graph might look something like so. Now, this is a directed graph, but we're also going to add one extra thing which will make it even more interesting, and that is that this graph is going to be weighted. And what I mean by this is that each of the edge that we have is also going to be given a number like such, and this number is going to be what we call the weight of each of the edge like such. And so now we have a directed graph where each of the edge will also be given some weight. Now I am going to assign two of the vertices as something called a source and a sink. I'm going to explain what it is in a second. So I'm going to assume that this here is a source, and this bit here, this one here, is a sink. Now you can think about this maybe in a more physical sense by maybe imagining each of these red dots being different places in a city, and each of the edges being a one-way road connecting one part of a city to another. And you can consider something called the flow of the things going between each of the edges. So you can imagine you have something starting, for example, at the source. It can take some path through and then comes all the way down to the sink. So you can think of many different things. So you can think of objects, maybe like a car or a walking person, starting from a source, taking their paths, and then going all the way to the sink. Now, the objects going from the source to the sink will follow the arrows that we have, or follow the direction of the edges. So, for example, it might go from the source, it might go down here, it might take that path there, and then go there, and then come down to the sink, for example. But it wouldn't reverse the direction of the edge that we have. Now, let's assume that each of the edges, or in our case, each of the roads, has got a maximum number of people or cars that is able to go through that particular road at any one time. And this is what we're going to be called the maximum flow of that particular edge. And they will be represented by these weights that we have. So for example, we're going to say that any one time this bit of the road here can handle at most 2 units of flow, and this one 1 unit of flow, this one 6 units of flow. You can also consider some other properties about the flows that you might have, that the flows must be conserved. For example, if some amount of flow goes into a certain vertex, the same amount of flow must also leave the vertex. And so the question of maximum flow is very simple, is that if we're given a graph like such, and we're given the maximum flow that is allowed through each of the edges, the question is, what is the maximum amount of flow that is allowed to go all the way from the source to the sink? So to give a better idea of, well, some paths that we might have, let's suppose I consider this path. So go from here to here to here. Well, ideally, the maximum flow that can go through this path would be 5 plus 3 plus 3, which is 11 units of flow. But it turns out that that wouldn't be the case here. Because if you look carefully at this vertex here, 5 units of flow goes in, but only 3 units of flow leaves this vertex. And that would violate the conservation of flow. So as you can see here, this edge of 3 units here is sort of a bottleneck. So really, you can't have 5 units of flow going into here. You can only have as much as 3 units of flow going into this part. And so really, the total units of flow possible for this case would be 3 plus 3 plus 3, which is 9. But it turns out that's not the maximum amount of flow that will be allowed in this entire graph, because this is only for one path. Each of the flow can also take some other path to get from the source to the sink. So the question is, what is the maximum amount of flow that you can take going from the source all the way to the sink? Now, there are many different algorithms that can be used to solve this problem. If you go on Wikipedia, you'll see a huge list of such algorithms. Even though they're interesting, they'll be left as a story for another time. The solution I'm really interested in for this particular video is to use the linear programming approach. And what we're going to do is we're going to try to turn the problem that we have and rephrase the problem as a linear program. And so this is going to be the graph, just as a reminder. And so we're going to try to write out a linear program which will represent this problem. Well, if we want to write this problem, the max flow problem, out as a linear program, we really only need to think about 3 things. First, we need to think about how we are representing the solution of the graph. In other words, what are the variables? What variables are we trying to change and adjust to get the maximum value? We have to find the objective. And in this case, the objective will be what we are trying to maximize, which in this case will be the flow. And lastly, we also have to find some constraints, because we can't just vary variables however we like. And so we have to figure out the constraints so that the flows that we get out still holds for our problem that we have. So let's go through that pretty much in that order. First, we are going to think about the variable that we have. Now, in this case, what we're really trying to change is the amount of flow that is going through each of the edges. And so it makes sense that we try to make our variable, well, as such. So how we can represent the variable is represent it as the amount of flow that will go through each of the edge of, well, this graph. So as a reminder, a graph that we have will have 2 things. It will have a set of vertices, and we'll have a set of edges. And so what we really need is we really need a variable for each of the edge that we have. And so suppose we can represent our edge as a set of 2 numbers, and we're going to say it's I and j. And the way I do so is by saying that if we have 2 vertices as such, and 2 vertices have got label ij, we can say that an edge going from vertex I to vertex j will be represented by an edge writing out like this as ij, like so. And so we want to represent the flow going from, for example, this vertex to this vertex, or the flow that will actually happen in this edge. We can use a variable. So we can say, use the variable, for example, f for flow. And we're going to say it's the flow from I to j. And this will be the flow going across the edge I, j in our graph. And so we're going to have one of these variables for each of the edge of the graph that we have. So this will be our set of variables. Our variables will just be a whole bunch of this. So we're going to have some flow across some edge, where this edge will be in the set of edges that we have. Now that we have the variables, we have to come up with the objective. And this objective should be pretty easy, because we're trying to find the amount of maximum flow that this network or this graph can hold. And so the maximum amount of flow will just be the sum of all of these, because this is the flow through one of the edges. So if we want the maximum total flow, it is just the sum over all of the f's. So the objective of this will be to maximize the sum of all of the flow through each of all of the edges, where ij will just be edges in E. Now, the last bit that we have to worry about, and will be the bit more complicated part, will be the constraints. Well, what constraints do we have? We have two key constraints that we have to worry about. The first constraint is the obvious one, and that is the maximum amount of flow that each of the edges can hold, because that is given in our question already. Suppose we have this edge ij like so. We can say that the weight, or the maximum flow we allow through each of the edge, will be represented by a w. ij as such. So one of the constraints will be that the maximum flow, the amount of flow that we have in maximum flow, will have to be less than whatever the weight is across that particular edge. So this will be written like this. This symbol means for all. So this is for all the edges in our set of edges in the graph. Now there's also one other, a bit more subtle constraint that we need to put in, and that is the conservation of flow, as I've mentioned earlier. So if we look at all of these vertex here, if we ignore the source and we ignore the sink, then if we consider any one of the vertex that we have, for example, maybe I consider, let's consider this middle vertex here. Then we know that by conservation of flow, if any flow goes in, all the flow must also go out. So it turns out that that is also another constraint that we need to put in. So let's suppose we have a vertex K. Then we have to say that the flow going into that vertex, which will be the sum of all ik in edges, and this will be fi of k, this will be the total flow going into some edge, will have to be equal to the flows going out of it. So this will be kj of edges fkj, like so. And this will be flows out of. So the math might be a bit confusing, but all this is saying is that the flow going into a certain vertex will be equal to the flow going out of a certain vertex, where k, for all k in the set of vertex, but we're going to exclude the source and the sink. And the reason we're doing so is we're assuming that the source and the sink are, well, not really like any of the normal vertex. The source can produce any amount of flow it wants, and the sink can absorb any amount of flows it wants. And so there you can see here, that's pretty much the linear program. Now, once we have the entire problem out as a linear program instead, we can throw it into one of the linear program solver algorithms, like the simplex method, for example, that can be used to solve this particular problem and give us out an answer. It's really simple. If we have a graph problem like this, as long as we can turn it into a linear program, we know that there will definitely be a way in order for us to solve the equation, and it's really good. Well, there's a couple of bad things of this particular approach. The key one is that methods of solving linear programs, like the simplex method, is said to take non-polynomial time, which is a really fancy way of saying it takes a long time to solve it. Compared to some other algorithm that is out there, this algorithm will be considerably slower. But the good thing of this approach is that we don't really have to come up with a tailor-made algorithm in order to solve this particular problem, because we know that as long as we have a problem and we can turn it into a linear program, we have a way of solving this problem. And no specific algorithm is needed apart from the simplex method, which makes it really simple, especially when you have other problems that you want to try to solve. As long as you can take that problem, put it as a linear program, you're going to be good to go. Many classic optimization problems, like if you have a certain amount of stuff, you want to sell it for maximum profit, a lot of the times those can be phrased as a linear programming problem. And if you can do so, you're going to be guaranteed that you can solve it. Are you a thief in a night museum trying to steal as much valued goods as possible while still remaining under the weight limit that you can carry? Well, that's what we call a knapsack problem, and that can also be solved using a linear program. You have a problem with a broken relationship? Well, as long as you can turn it into a linear program, well, the simplex method can probably help you with it. But most importantly, if you have a graph problem like what we have, as long as you can turn that graph problem into a linear program, you're going to be able to solve it using the simplex method. Think of the simplex algorithm a bit like a jack of all trades. As long as you can take your problem and phrase it as a linear program, the simplex algorithms can always solve your problem. So now let's go back to our problems of flows. I almost forgot that we had to solve that. So flows is maybe some sort of a graph problem, or at least you could probably try to see it that way. And if there is no good graph algorithms that you can come up with, maybe you can give linear programming a go. So what we can try to do is you can try to take the problem that we have and then try to phrase it as a linear program. Find the right constraints to give our solutions the way we want. This was the picture I showed you right at the very beginning. This is what we're trying to find. We're given all of these colored dots and we're trying to find the path, the connection that we should make for each of these, well, to connect to each of these different colors. And so, as I mentioned, we should try to consider out this problem as a graph. And so, this is exactly what we are going to do. Now, for this part, I'm not going to spend so much time on actually writing out the mathematical formula, but just show you what sort of constraints I will be putting on. If you're interested in the actual code, in the actual equations, check out the description. I'll leave you a link to my GitHub, which I'll have all the codes there for you. So first, let's talk about what variables I need to consider. Well, for each of the edges here represents a line going from one point in the grid to another. So these edges represent each of these edges, and each of the edges we have a different color to represent it. And so that's what we can do. We can take one edge and we can find a variable that represents, well, what color we paint that particular edge. So for example, we let the edge be represented by two numbers, I and j. This will be the edge connecting vertex I and vertex j. Then we can represent this edge using a variable, maybe x, I, j. But it turns out for this case, for our case that we have, just xij like this will not be enough, because we're not only trying to paint the edge, we also want to know what color we're going to be painting those edges. And so we might need an extra, well, index. And so rather than representing the edge as xij, I'll represent it as xijk. And the reason we have the k is so that we can also show what color we're going to paint the edge. So the way I'm going to define this will be that xijk will be 1 if the edge ij is painted color k. And I'm going to say it will be 0 otherwise. Now, a couple of you might be a bit annoyed that I'm letting my variable only be between color 1s and 0s, but I will assure you that it is perfectly okay to do this. In fact, our problem is no longer really a linear program. It is what we call an integer linear program, but it is perfectly okay. For the purpose of this video, we'll just ignore that fact. So now we have a variable xijk, and this represents each of the edge. Now, it turns out that we also need another variable set. There might be a way to do this without this other variable set, but I decided to go with it because I really couldn't think of any other way. And rather than also representing each of the edge, we're also going to try to find a way to represent each of the node, which represents each of these blocks. Because as you can see here, if we have an edge connecting like this, then all of these nodes in this path will, in a way, be painted the same color as the path itself. So for example, that will be painted red. This bit here will be painted blue like that. Really lazy to color the whole thing in, but you get the point of what I mean. So each of the particular node or the vertex, as I've been using in the entire video, will also have some sort of a color. And so we can use another variable to represent it. So each of the vertex, in this case I'll say vertex I, and each of the vertex I will also have another variable to represent it, representing what color it is, or what color of the path passes through it. So the way I'm going to do so is I'm going to say another variable. I'm going to say y of I, and again, because one vertex can be many colors, I'll say yik, and this will be equal to 1 if I is painted color k, and it'll be 0 otherwise. So now we have two sets of variables, one to represent each of the edges and one to represent each of the vertices. And of course, we'll also have the colors of each of the edge and each of the vertices. And this will be all the sets of the variables that we have. And I'll draw just line up there so you know that this are the variables. So now we have to come up with our constraints. So what the problem needs to look like for us to consider it valid. So we can put in some of the obvious constraints in, right? So because we know that one particular edge can only be of one color, that will be a pretty obvious constraint that we can put on. So if I pick out, for example, one of the vertex, then we know then that vertex can only be of one color, which means that if we do a summation of xij over all of the k in colors, then this can only equal to 1. Like so. This will be one of the constraints, and this applies for all I, j in the set of edges of our graph. This ensures that one edge can only be painted one color, but it turns out that is not particularly true, because sometimes, as you can see here, we have some edges which turns out to not even be colored. So it's not really equal to, it is less than or equal to, like so. And the same thing can be done for the vertex. If we take out one particular vertex, we know that one vertex can only be painted one color. And so we can also do that as well. We can say that the sum of colors of yik will have to be equal to 1. And that must be an equality, because we know that all of the nodes, all of the vertex must have some color. At least that's what the game really wants. Now we can start to get into some of the more interesting constraints that we have. For example, let's consider one of the vertex pairs like this. So let's consider one of the edge. For example, we consider this particular edge. If this edge were to be blue, then we know that these two of the vertex, or these two nodes, must also be blue, like so. And that turns out can be put out as a linear constraint, which I won't really write down, but that is one idea that we need to also encode into our linear program. The constraint, without writing the whole thing out properly, will look something like this. We say that the edge with a certain color will be 0 if either of the nodes is not of that color. You can think about this, why this must be true. I won't really show how this is turned into a proper equation form like this, but just ensure that this can be done. Now there's also another constraint that is also important, and that is in terms of which edges are painted coming out from a particular node itself. So we consider, for example, this node, which might be painted whatever color. For the purpose of this, let's assume that we found out that this is going to be a red vertex, like so. Then we know that if this is a red vertex, or this is at least one of the vertex that will be painted red, then we know that there must be two edges that is red color going from it and to it. You can also consider here, these two edges were the edges that was not given to be red, but we later discovered that it should be red. And for this one, there is two red edges going away from it, and this one, there's also two red edges going away from it. And so if we have one of the vertex, which we know is going to be of a certain color, there must be two edges of that color leaving it. And again, that can be written out as a linear constraint. If you want to write it as a constraint, it might look something like this. Very sloppily, if a vertex is painted a certain color, then there must be 2 edges of that color going away from it. Now, another case we have to consider is the case where we already know, for example, we are given that if this is given to be a node of a certain color already, or in other words, we know that this is, for example, one of these nodes. And if we know that it's one of these nodes, then there can only be 1 edge leaving it, right? Because if we are given a color, then it is sort of where the start or the end is, and there can only be 1 edge leaving from it. Well, if you know that an edge is of a certain color, then that's really good. Then you can, in fact, even write this constraint out properly. You can say that if this is a certain color, say color K, then we can say that y of ik must be equal to 1 if this is color K. Like so. Then you know that the sum of jk of xijk must be equal to 1. In other words, only 1 edge can be going in or out from it. And this is the set of all of the constraints and all of the variables that we need for our problem. Now finally, we have to come up with an objective, and this one is a bit strange because it turns out there's nothing we're really trying to maximize in a sense. There is not like a maximum score we're trying to get or anything, so really there is nothing, well, to really maximize, because all we're really interested in is just a solution that works, not any particular solution that gives the best way of working or the highest score in some sense. However, for us to be able to put in the solver, we do have to come up with an objective, so we just picked any old random objective. And so there we have the problem there, as I've mentioned. I know I haven't really phrased my constraints as actual mathematical operations, as actual mathematical equations, but I assure you that you can in fact turn those expressions I've said into linear equations so that you can put it in the form of a linear program. And obviously then I can just throw it into a simplex solver and then use it to find the answers of my problem. And so, for example, now if I have a flows board, a problem looking like this, I can first turn it into an array of numbers as such, and I can throw that array of numbers into the program, and the program will just spit out the correct answer. And as a little cherry on top, I also wrote some image processing programs so that I can just throw it an image screenshot of the problem that I have as a picture file. Then it'll read the picture, figure out the charts for me, and then it'll just give out the actual answer drawn on the picture like this as well. So that was a project I've been sitting on for about 3 months, in the sense that I had it completed like quite a while ago. I just never really found the right time to make this video and release it to you people. And if you want to check out the notebook that I wrote this problem in, you can go into the description. I'll have a GitHub link where you can just go look at the notebook. The notebook is written in a language called Julia. I know I use Python a lot on this channel, but I use Julia in this case because it's quicker and I really like their optimization package. But anyways, I think that's will be the end of this video. Thank you very much for everybody for watching, and have a great day, I guess. It's not raining over here, so yeah, I guess I'll see you in like 6 months or something, I don't know.